let's prove that the sum of the first n square numbers, so that's the sum from 1 to n of r squared, gives us this result. 1/6 n brackets n plus 1 brackets 2n plus 1. So this is a standard result in A-level further maths, but we would actually like to prove it today. We're going to do this by induction. So like all proof by inductions, we start with the case where n equals 1. This should be really simple, just a bit of computation for us. So if we look at the left-hand side, that's this part here. And what the left-hand side wants us to do is just look at the series from r equals 1 to 1 of r squared. Luckily for us, this is a very easy series to think about. It's just got one term, and it's 1 squared, which is of course 1. Well, let's also look at the right-hand side. That's this part here. And if we substitute 1 into here, we've got 1/6 times n, which is 1, n plus 1, which is going to be 2, and 2n plus 1, which is going to be 3. We've got 1/6 times 1 times 2 times 3, which is 6. So we've just got 1 in the end. Great, it's true for n equals 1 then. Let's write that down here. True for n equals 1. The next step of any proof by induction is assuming it's true for n equals k. So we want to write that down below. Let's assume true for n equals k. And what's a good habit for us now is to say, well, what are we actually assuming to be true? And namely is this: the sum from r equals 1 to k of the r squareds will give us 1/6 k, k plus 1, 2k plus 1. Next comes the inductive step of a proof by induction. And that's us saying, well, if we think it's true for n equals k, what about for n equals k plus 1? So n equals k plus 1. We would like to show that this result is also true for n equals k plus 1. We're not allowed to use it as being true yet though. Let's show what we would like to have. So I'm going to write in a different colour because we can't really use this yet. We want, amongst a lot of other things, we want this. So the sum from r equals 1 to k of the r squareds is going to be 1/6 k plus 1, because our k has now become a k plus 1. Our k plus 1 will now become a k plus 2, and I'll have to squeeze this bracket in below. But our 2k plus 1 is now going to be 2 lots of k plus 1, which is 2k plus 2, add another 1. So it will be 2k plus 3. We would like to show this. The way we're going to show it is with a similar idea that's used in a lot of proof by inductions. We're going to take this series, which is the sum from 1 to k, and then we need to add one more term on the end. So let's show what we mean. The sum from r equals 1 to k plus 1 of the r squareds, well, that's equal to the sum from r equals 1 to k of the r squareds plus one more term on the end. And our one more term on the end is going to be k plus 1 squared. So we've taken what we already know. It's true for r equals k, sorry, n equals k. And then we're adding this one more term on the end, and we'd like to get this result that we've said down here to be true. Our job now then is to make this thing here look like this thing down here. First of all, we should write this series in terms of the result that we know. So for us, that's the sum from 1 to k is 1/6 k plus 1, 2k plus 1. And we can't forget to add on our last term at the end. That's k plus 1 squared. Okay. Next step is for us to be a bit creative in how we factorise this side. If you have a look, we've definitely got a k plus 1 in each of these. So let's first of all take out the k plus 1. But being a little bit more clever, we can also take out a 1/6. The reason for this is it's going to be a lot easier for us to operate inside this big square brackets with only whole numbers. So taking out the 1/6 and the k plus 1 leaves us with here having a k brackets 2k plus 1. And over here, we've still got a k plus 1, but we actually need a 6 in front of it, because then the 1/6 and this 6 would multiply together to just leave us with the 1 from before. So we've kind of deconstructed this to give us that nice 6 in front. It's going to be really helpful for us on the next step. Let's have a look then. As we expand this out, we should get 1/6 brackets k plus 1. And inside our big square brackets, we've got 2k squared plus k plus 6k plus 6. At this point, we need to gather these terms up, the 2k's here, make it a quadratic, and then hopefully solve it, or at least factorise it. 1/6 k plus 1, that doesn't change. And we've got 2k squared plus 7k plus 6. How can this thing factorise? And I wonder if it will look like what we're after. Hopefully it does. We've got 1/6 k plus 1, 2k squared plus 7k plus 6 should factorise for us to give 2k plus 3 and k plus 2. You can check that for yourself, but it works if we look back, right? 2k times k gives us the 2k squared. 2k times 2 gives us 4k. 3 times k gives us another 3, which gets us 7k. 3 times 2 gets us the plus 6. That factorises fine. I would just like to write this out the other way to see how it looks just exactly the way we'd like it. 1/6 k plus 1. Let's write the k plus 2 here. And then 2k plus 3 can go on the end. If we have a look back at what we wanted earlier, we wanted 1/6 k plus 1, great. K plus 2, great. 2k plus 3, also great. So what we've showed is that this rule, if it's true for n equals k, it must therefore also be true for n equals k plus 1. That's the form we wanted. So let's write below. So if true for n equals k, then, it's a bit messy, true for n equals k plus 1. And the real magic of proof by induction for us is that this line, if true for n equals k, then true for n equals k plus 1, combined with it being true for n equals 1, means that it must be true for all the natural numbers, Because if it's true for 1, it's true for 2, then it's true for 3, and it's true for 4. So we can conclude at the bottom with therefore, so if we put these three dots like this to mean therefore, true for all, and I'm going to say all the n are natural numbers. So that's written like this. N, E, like this curly E means within the set of, and natural numbers we write like this, a kind of chunky n.